Welcome to another video. We now know basically everything about martingale convergence, and actually this will be the last video on martingales, but this time we will consider continuous time. We already had some processes in continuous time, namely the Poisson point process and Brownian motion, and we will start today with saying something about martingales connected with these two processes. And later in the video, we will see how all the results on martingale convergence and other stuff like the optional sampling, optional stopping theorem carry over to continuous time. So let's start. So martingales in continuous time. Let's first start with martingales derived from the Poisson point process. Actually, let me mention, so here it's the Poisson point process. On the next line we will have Brownian motion, and we will have some martingales connected to these processes. But we will even have more martingales connected to any Markov process in the chapter Markov processes, which is the next chapter. So here there are just some examples. So here for the Poisson point process, so remember, that's a process where increments are independent and Poisson distributed. And for the Poisson distribution, so if I have something like, well, maybe not x, but some z equals Poisson lambda, I have the expectation of z equals lambda, and that's also the variance of z. That's important. So first I claim this here is a martingale. So I consider s smaller or equal to t, and I have to see if the expectation of xt minus lambda t given fs equals xs minus lambda s. And all I'm doing here is I write xt as xs plus xt minus xs. That's apparently the same, minus lambda t given fs. Well, xs is fs measurable, so I can write that already. xt minus xs is the increment which is Poisson distributed and independent of fs. Okay, so I can forget about the fs, and that's lambda times t minus s minus lambda t equals minus lambda s, and I'm done with this here. And I've shown this here as a martingale. That's actually not so surprising because xt on average grows like lambda t, and if you subtract that, well, it's a martingale. The second one is this here. So the increment between time s and time t is xt square minus xs square, and I have the integral here, and I can say it's integral from s to t over 2xr plus 1 dr. And that's the increment, so I have to show that the increment given fs is 0. So I have to show this thing here is 0. How do I do this? I do it first with a usual trick. So xt minus xs square, that's of course not xt square minus xs square, that's xt, but I can correct this by writing plus 2 xt minus xs times xs, because now xt times xs, well, that also appears here, and minus 2xs square, well, I exactly corrected this here. And of course I'm doing this because xs is fs measurable and xt minus xs is independent of fs. Okay, and for the rest, minus lambda s to t, and here again I'm writing xr a bit funny, xs plus xr minus xs plus 1 dr given fs done. Now that's the second moment of a Poisson random variable. The variance is the parameter, which is lambda times t minus s. But the second moment differs from the variance by the square of the first moment. So I have plus lambda squared times t minus s square. Okay, I have 2xs here, and the expectation of xt minus xs, that's lambda times t minus s. So that's the second bit here. And in the third, okay, I have an xs here. So xs plus 1 I have here, given fs. That's fs measurable, minus lambda 2, lambda 2xs plus 1 times t minus s, because that's the integral here. xr minus xs is independent of fs. So I have to integrate lambda times, so 2 times lambda times t r minus s. And r from s to t. So side note here, I have integral from s to t lambda times r minus s dr, which is the same as the integral from 0 to t minus s r dr, and I forgot a 2 here. And well, that's lambda times t minus s square. Yeah, and this here, together with this lambda, gives minus lambda square t minus s square. And as you can already see here, that goes away. What else? Did I forget about something? No, here I have the plus 1, which comes with the lambda and t minus s. That goes with this. And all the rest has an xs, a lambda, a 2, and a t minus s, with plus and with minus. And I'm done because this is now 0. Okay, very nice. So we have shown that these two things here are martingales. And we come to Brownian motion. Here we have 3 martingales. Alpha times xt, alpha xt square minus alpha t. And here something which we will be dealing with also in the next 2 slides. E to the power of something. Again, for s smaller or equal to t, okay, the first one is pretty easy. Alpha xt given fs. I'm doing the same trick as I did on the last slide. Alpha I can write before that. Xs plus xt minus xs given fs. Xs is fs measurable, and xt minus xs is independent of fs and normally distributed with mean 0, which means it's either plus 0 here, and I'm already done. Then the second one, expectation of alpha xt square minus alpha t given fs. Again, I'm doing the same trick as on the last slide. So alpha I can write before that. I have xt minus xs square plus 2 xt minus xs times xs. So when I combine this, I have xt square, that's what I want to have, minus 2xsxt, with minus here and with plus here, and I have plus xs square minus 2xs square. So I have to compute plus xs square plus, minus t given fs. So that's the second moment of a normal random variable. So that's alpha times t minus s. In the second term, I have that xt minus xs is normally distributed and independent of fs, so that's 0. That goes away. Xs square plus xs square minus t. Well, and that's alpha xs square minus alpha s, and I'm done. And the third one, this exponential martingale here, I can write the expectation of e to the alpha xt minus alpha square t over 2 given fs. Again, I'm writing the xt here as xs plus xt minus xs. So the e to the alpha xs I can pull out, minus alpha square t half. And I'm left with the expectation of e to the power alpha xt minus xs, which is independent of fs, so that's just like this here. And of course, that's nothing but the exponential moment of a normal random variable. So I get here e to the power alpha xs minus alpha square t over 2. And when you use the characteristic function of this thing here, you get that this here is e to the power alpha square t minus s over 2, which in the end gives me e to the power alpha xs. The minus alpha square t half goes away, and it stays alpha square s over 2, and that's exactly the same as this here at time s, and I'm done. And now that's very nice. So this here is a martingale on the one hand side. So which expectation does it have? It has expectation 1, because if t equals 0, I have e to the power of 0, which is 1. So the expectation is 1 all the time. So a non-negative function with expectation 1, so that's a function which integrates to 1, so that's density. And for this reason, so I'm starting with my probability measure p. So that's here is the expectation with respect to my measure p. But I can define a new measure which has this density with respect to p. So that's another probability measure. So let's see what that does actually. You can guess that a little bit. So if the density has a high number, that becomes, so such paths become, get some more weight. So where does it give more weight? Well, if x tau is big. So under p, you could say, well, this path and this path and this path maybe have the same probability. There's also a chance that they have something going up. But under the Q measure, that path here which goes up, that gets a higher weight. So that gets a higher weight than all the others. because it has a high value for the density. So keep that in mind. And for the next slide, we need some more notation. So a Brownian motion, it's clear that's what we had. But I can add a drift here. Xt plus mu times t. I can add a drift to my Brownian motion. And then I call that a Brownian motion with drift. That's a martingale if mu equals 0. And if mu is bigger than 0, it's a submartingale. And if mu is less than 0, it's a supermartingale. By the way, I assumed here in my explanation that alpha here is positive. And then it gets a large value, so the path gets a large value if it goes up. Keep that in mind for the next result here. I have two processes here. X equals my Brownian motion defined on my usual probability space omega of p. And I have y, which is the Brownian motion with drift mu. And I have the probability measure q from above. Well, so the density here, so the density is e to the power mu xt minus mu square t square over 2. That's this density here. Then, well, that's funny here. So this random variable x under the new measure q, well, we just saw with if mu is positive, then such a drift here gets more weight, and for that reason the x star under q is the same as the y star under p. So these are two distributions here, and y star under p is the distribution of a Brownian motion with drift mu. And x star q, so that's the distribution of x under a probability measure q, where we re-evaluate the weights and we give more weight to paths which go upwards. So it makes some sense that that becomes a Brownian motion with drift, but that's a very complex notation for what happens here. So let's try to see how that works a little bit at least. And I'm going to show you this here. So if these two things are the same, the q expectation of f of xt should be the p expectation of y at time t. Okay, y is xt plus mu t, so the q expectation of this is the p expectation of this here. So that's one part of this equation here. So how does it work? So I want to compute the q expectation of f of xt. Okay, q is the measure which has this density with respect to p. And actually for the density it doesn't matter which t I'm plugging in here, because I have a martingale. So if I have that for some tau and tau is bigger than t, I could just condition on ft, and I'm using then the martingale property that the right thing here happens. So I'm getting this here. Well, an xt has a normal distribution under p, which means, well, here it's just a normal distribution. So xt is my mu, is my y here, f of y e to the mu y, and that's the density together with this thing here, and e to the minus mu squared t over 2 is written from here. Okay. How can I do this? Well, I have to evaluate the integral in somehow at least. And I'm having a y square here and a y here. And I can do the following. I can write this here. I have a y minus y squared over 2t here. I have a plus mu yt divided by 2t. So that's mu times y, which is exactly this thing here. And then I have a minus mu squared t squared over 2t, which is mu squared t over 2, which here comes with a minus. So I have to correct it here. And okay, this thing here I'm just writing down again. But as we already see, that this term here goes away completely. And now I can just shift the y here by mu t, such that I get this here. And re-evaluating this here, okay, that's just the expectation of f of xt, which is the y here, plus mu t. And we have shown what we wanted to show. And in the manuscript you can read it a bit in more detail, but that's the basic thing here. So let's come to the last topic of today and of the martingale part, which is a general results on martingales in continuous time. So basically, in the next slide here, we will say the usual conditions hold, and we have to say what that is. Then basically all interesting propositions, theorems, and corollaries also hold in continuous time. So what are these usual conditions which are so nice? That's the following. The filtration is right, continuous, and complete. Okay, we already had that. This could be a nice thing. Filtration right, continuous, and complete. And each submartingale has a modification with cut-luck paths. And the second thing here is actually proved by this result here, which I'm not going to show the proof here, but the following is true. I have a submartingale and y equals x at rational times. Then there is a null set n such that yt plus is this, so this limit here exists, and the process z here is a submartingale. And if the filtration is right continuous, which will be the case if the usual conditions hold, then x has a modification with paths which are cut-luck if the map from t to the expectation of xt is right continuous. So this thing here seems to be a crucial property. T maps to expectation of xt is right continuous. Of course, if x is a martingale, that's even a constant, so that's then also, of course, right continuous. But for submartingales, it's not so clear if that must be right continuous. Okay, so that's it. So what do we need? We need that this here is right continuous. Then I take the modification with paths which are cut-luck. And then, yeah, well, I just take this, I'm able to take this modification, and then, so these usual conditions then I assume are holding, then all the rest here follows. So that means basically for us in the remainder of this lecture, once we assume the usual conditions, we are allowed to use martingale convergence, optional sampling, optional stopping, also in continuous time. Okay, and that was it for the martingale part of this lecture. And next time we will start with Markov processes.